Hi guys, and welcome to part 2 of our information extraction video set. In this section, we'll cover mostly named entity recognition, but then a couple of examples of things of how you can begin to tag your own sets and create relationship extraction data sets. So in general, NER refers to extracting named entities out of text. If I Googled, where's the Tribune Tower? It first has to extract the entity out of my sentence, Tribune Tower, then find the answer. So NER is very important for a lot of question and answering systems. And typical entities that you might find are persons, laws, dates, money, products, businesses, and locations. There's even more, like sporting events. And so you must be able to do entity recognition to be able to do entity relation and event extraction. So a lot of more complex tasks in information extraction, like adding dates to your calendar automatically, require these lower level tasks, although not easier, but lower level tasks like named entity recognition. Okay. It's also very useful for machine translation because you wouldn't translate the entity names. And so let's look at some base level NER from spacy. So there are pre-trained models in spacy that you can use. And we can use spacy to train our own models as well. And so the biggest issue with that, you think, okay, great, I'll just build my own, is that the text data that's required to do an NER is very time consuming to build. Okay? And so that's why potentially we could use some labeling systems like CONLL or grab pre-trained data and add our own components to it. Now, if we just want to get the automatic extraction from spacy, we could import spacy, load one of their language models, process it, and then print it out. So to get the entities, you loop over the ints, E-N-T-S, and print out int and int.label. So we can see from the history of NLP that my text is pulling from the last lecture. We have several dates, 1950s. Notice how one is the and one is just 1950. Alan Turing is a person. Intelligence as a work of art, although it's probably listed as artificial intelligence. So that one's probably not correct. These systems are not perfect. More date, more than 60, which is a number, right? Russian, which is a nationality, English, which is the language, right? So we can see that we get a good number of things pulled from here. Okay. It also is coded NLP as an org, when that's just simply an acronym. So I want you to see that the World Wide Web is maybe not a work of art. So the pre-trained systems are good, but they're not perfect. And so we could maintain our own list of entities that I wish to extract with their labels. So I'm looking for product names for my business, or I'm looking for other competing businesses, and I have a list of things that I want and those labels. Okay. Then you might have to add new ones to that system as you go. You'd have to deal with different forms of the same name. So USA and United States of America are all the same entity, right? And a lot of folks use what's called rule-based NER. And so you keep these lists, these kind of rules put together of what to extract, as opposed to machine learning types of systems. And so one of the rules might be extract any proper nouns or extract any cardinals, which are numbers, okay, as a marker for the entities using part-of-speech tagging, which we saw in the last lecture. Okay. So we could use those kinds of rules, or we could use machine learning. Okay. And the issue with machine learning is it takes a lot of examples, and the NER really actually is more about extracting phrases sometimes, like New York City, as opposed to just New or just York, okay, and not the individual words. So sometimes it's hard because the tokenization may lose those entities, and so it becomes a lot harder to distinguish new, something is new, and new from New York. Okay. So most systems are a mix of rule-based learning and machine learning. Okay. And the other issue for machine learning, traditional machine learning, is that context is really useful for NER, which is one reason why some of it depends on dependency parsing, which uses context. And that can be hard for machine learning. Now, newer neural net systems can handle context pretty well, but we're still dealing with extracting specific phrase level items. Okay. And so the solution for context, especially when it comes to machine learning, is to use what's called a conditional random field or a Markov model, because these are sequence classifiers. So sequence classifiers examine items in sequence and can grab chunks of items. So Markov models and conditional random fields are both types of sequence classifiers. So let's talk briefly about conditional random fields, and then we'll do an example of training our own system. Okay. It is easily the most popular sequence classifier, especially for NER. So if you Googled conditional random field, you would find that it says next to it almost every time, this is very popular for NER. Okay. So we'll use scikit-learn CRF suite, because for some odd reason, scikit-learn doesn't have conditional random fields, which is unusual. Okay. And then we'll use the CONLL 03 dataset to show you how you might train this. Okay. And that dataset is programmed with what's called a bio or BioLU system. And so these are tags for each individual token to help us extract chunks of information. And if you look at the old NLTK book, this is actually called chunking, which I find wildly amusing because that's a cognitive psychology term for putting things together into little groups so that you remember them better. So for example, we always say phone numbers as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Or your social security number in little chunks. And that's because psychologists have said this is the best way to remember something. And so this biosystem, beginning inside, outside, uses that set of codes to tag so that it can be an entire phrase rather than a single token at a time. And we'll see what that output looks like in just a second. Okay, so bio, beginning of the entity, I inside the entity, so a word in the middle, and O outside the entity. And so what you would extract from your text is anything with a B or an I. Okay. And that helps us to know where to start and stop phrase extraction. Okay. So this is from the textbook. It's I've got the Practical NLP GitHub link here in case it needs to be updated, but these are all the packages that we'll use here. So scikit-learn CRF suite, NLTK for part of speech tagging, scikit-learn's metrics, pretty print, right? Pipelining, strings, iter tools, counting, regular old scikit-learn, and flatten. And we'll talk about why the flatten is important in a minute. If you take this code directly from the book GitHub, it will not run, but I'll show you how to make it run. Okay. So this data is from the Conference on Natural Language Learning. Okay. It's a widely used data set for named entity training. Okay. And the article about the data set can be found here on the ACL anthology. Okay. Other data sets are available for other types of entities. So this is a more generalized entity training data set. There's also one from Wikipedia, but there's one for medical terminology, healthcare terminology, and even Wall Street terminology from Wall Street Bet's Reddit threads. Okay. So there are other data sets. And one thing that you'll see as we go, and I'll probably say 5 times too many, is that NER data sets or NER implementations are very brittle, meaning they're only good for the data that they're trained on, and even that may go stale fast. So let's load this data set. And this is included with the zip file for the notes. Okay. And so there's a training data set and a testing data set. And so let's just open one of those and look at it. And one of the issues is that this is a text file. So if we want to put this into a format that we can use to actually train our data, we have to loop. So we've opened the file and I've just printed out the type because it will show you that you have to do something else to get this into a proper format. Okay. And so, oh, this didn't print properly, but the example format for the data is EU. Okay, this is B, the beginning of the chunk, and it's an organization. Rejects is a word that is outside the chunk. So I have a beginning here. There's no marker for end because there's only one word. German is B-misc. For a lot of times this is labeled as geopolitical entity. Okay. Call to boycott are all outside chunks, so they would be excluded. British, considered misc as well. Lamb, outside chunk. Okay. And so this is how the data set is laid out, one line at a time, where each token gets its own row and it has the label next to it. So in all practicality, this is essentially the feature and the label. It's a very simple prediction algorithm, but we want to use the information of the context of the words around it to help us predict. That's what makes it a sequence algorithm, as opposed to a log regression or naive Bayes, which would ignore the sequence of the words. So a function to read the data in and put it in the right format was provided with the book, but let's see what it does. Okay. It creates 3 little mini lists, my output, words, and tags. It opens the text file and then runs through each line one at a time, which is why the text files require looping. Okay. It strips all the extra stuff at the end of the line. And this is specific to this data set here, but basically, if there's no tab, okay, that basically means that the line's over. So deal with it in a different way. But if there's no tab, just stick the words and the tags, okay, from our loop here into a little list. So it will end up being a list of lists. Okay. Else, the word and the tag are split on the tab, okay, and it will add the word to the words and add the tags to the tags. Okay. So what happens is for each sentence, remember there's one row, back up, one row per token. So until you get to the last one, there are tabs separating them out. So we've created a little place to hold word tag, word tag, word tag. So we have a list of words and a list of tags, and they're matched to each other, where the first one is the first word and the second one is the tag. Okay. If the sentence is over, it sticks that into the output section. So what you end up with is a list of lists. So each sentence is a list of words and a list of tags. Okay, so it's like a list of lists of lists. So each mini list is a list of words and a list of tags. Okay. And so let's look at that. So to make this a little bit clearer, so we've loaded the training data and the testing data. And here, oh, I gotta find it. Here's where it ends. Okay. So first one, EU rejects German call to boycott British lamb. Okay, we've got the list of tokens, the list of tags, here, and this is where it ends. Sorry, I highlighted too much. So a list of tokens, a list of tags. And the next one, a list of tokens, a list of tags. Okay, the next one's just one name. Okay, and so some sentences are not very long. And then we've got Brussels, right? So this data set doesn't necessarily have like full sentence structure all the time. And so that's kind of a nice format because it deals with the fact that this is not square, right? So what that means is I can't really put this in a pandas data frame and hang on to sentence structure. I could put it in a pandas data frame straight from the text, right? Because I have one column for token and one column for tag, but I can't hold on to the order. There's no other marker that the sentence is over. So by putting this into a list of lists, that allows me to hang on to those sequences. So here's our first set of sequences. Here's our second set of sequences. And so each classification component becomes the sequence as opposed to the individual word. Okay, and that is more important, is the sequence here, as opposed to the actual words we're looking for. So it's using sequencing to train as opposed to using the individual features of the words. Okay. So it doesn't learn that EU is a tag. It learns that often sentences start with a entity. Okay. So how might we train this? Well, we can use any number of ideas once we have the sequences built from machine or deep learning described in that first week of class. But I want to go over, because we actually haven't done classification yet, the basic idea behind training algorithms and what we can do to determine if they're any good. So we're going to go middle machine learning section, and then we'll cover it a lot more in the actual like classification section. Okay. It's just some basic steps that you might do when you use machine learning algorithms. Okay, you separate the data into a training and a testing data set. You don't want to train and test on the same data. That's cheating. Okay, your model will look really good because you've trained it to the test. Okay. Then you need to normalize the text. This can be any other number of things. So the CONLL data is cleaned already before it got to us. But if it didn't get cleaned, we would need to clean it. We didn't need to arrange it in the right format, which we just did by putting it in this list of lists. And that's very specific to this conditional random field algorithm. And so what I find sometimes the hardest thing to do is to process the data to get it in the right format with the right feature extractions for whatever algorithm is happening. Okay, algorithm part's easy. I think people think that that's the hard part. Applying the math is easy. Getting it into the right structure is difficult. Then we'll do what's called feature extraction. So that's where you come up with what the predictors should be, because all machine learning boils down into predictors and outcomes, even deep learning. Okay, predictors and outcomes. So what are our predictors going to be? What might we use to predict if it's an entity or not? Okay, we could decide to use that if it's a proper noun or not. That actually makes things a little easier, and we wouldn't need a sequencing algorithm. But not all entities are proper nouns. Okay. Then in our case, we can use the sequence of the data to predict it, and there's even more. Okay. So this is basically just a fancy form of math. So how are we going to convert our text data into numbers to do the math? And so you have to think about what might be predictive of the outcome. So if I was trying to predict spam data on YouTube, which I have used for as a long time for a classification example, one of the best predictors is if the comment includes a URL. And so I seriously could just code all of the data as either has HTTP or not. And that would be very useful and actually would work pretty well. And so you need to sit down and think, like, don't just look at what other people suggest as a feature algorithm extractor, because if you look that up for NLP, it's going to be TF-IDF, which we haven't gotten to yet, but we will. Instead, think about like what might be predictive of the outcome. Like, what would I use mentally to know that this was an entity? And you're like, I just know it. Well, you don't just know it. It's usually because it's a proper noun and you've heard it before. So how can I get that information out of the text? Okay, it could be frequency. And in our case, it could be the sequence. Okay. Once you've extracted that information, you combine that extracted information with the labels. So this obviously requires labeled data. This is supervised learning. And then you apply some sort of algorithm. Log, Bayes, random forest, pick your favorite algorithm. Okay. Once that model has been tuned, you will apply the model to a testing data set, and that will tell you how good it is at generalizing to new data. So a model that runs really well in training data and does not generalize to testing data is a useless model, right? Because the whole goal is to build a model that works in multiple scenarios so you can use it in multiple scenarios. Okay. And we'd evaluate model performance. Now, I want to say this is from an LTK's book. I don't know. I found this picture somewhere and I love it because it's a really great depiction of all the different things that go into creating AI for NLP. Okay, even what I would consider a simple task, like predicting spam versus not, a 2-class scenario with some text. There are lots of options. And I don't want to say it's easy as in, oh, anybody could do it, but I'm saying like that is a task that is easy to put into a Medium blog. And so you can train one pretty quickly. But then obviously things can get very wild very fast. So either way, we have these training and testing documents. All documents must go through some sort of normalization. And this might just be spell checking. It might just be lowercasing. It might just be making sure the data is actual sentences. Okay. Or it could be totally crazy. You could remove all the stop words. You could remove all the numbers. You could remove all the punctuation. You could put it into all kinds of formats. Feature extraction, we'll talk about a lot of these throughout the semester and throughout this lecture, actually, where there are different features that might be interesting. So for NER, that again might be proper nouns, it might be the order, or relationship linking, that could be specific words. Okay. So you extract those features. We pair them with some sort of algorithm. Okay, and that builds the model. So when someone says, I built a model, what they meant was they went through all these steps, and now they've paired their predictors, their outcomes, with some sort of math that links the two together. From that classification model, I use that on my testing data, and I predict it. And I compare what I guessed as the new testing labels to the actual testing labels. And I calculate how well I did. If I did really well, the model might be good, and I can use it for something else. If I did really bad, I go back to the drawing board. Okay. And so to evaluate the entire model, you can use accuracy, just global accuracy. And this is exactly what it sounds like, the number of items you got correct. Or you can look at each individual label. And I don't want to say or, and look at each individual label. This is a really important step because models can be accurate and totally worthless. Because if you're trying to predict something with a heavy imbalance, for example, let's say you have 10 yeses and 1 no in a very simple model. Okay. If you guess that all of them are yes, your model will be very good. It'll be 10 out of 11. Okay. But you never got the no right. Okay. Now that's a really silly example, but it is an important component to looking at these classification reports is thinking about how good is the performance on each label, and do I care if the performance is really bad on one of the labels? Okay. And to do that, we can look at precision, recall, and the F1 score. I'm going to talk about each one of these on a different slide. Okay. To explain what these are, I'm going to back up and explain what's confusion matrix. So confusion matrices are a great way to explore how your model predicted certain categories. Okay. The problem with a confusion matrix is you have to do one category versus everybody else one at a time. And so if you have 15 categories, that's a lot of matrices. Okay. You can also build a multi-way confusion matrix, but they can get hard to read. But we're going to use confusion matrix as an explanation for how these scores are calculated. Okay. And what it does is it denotes the predicted label that you gave it from your model to the actual label in the training or testing data set. Okay. And so that's a great place to see where the model's getting it right and the model's getting it wrong, because that may give you the information you need to tune to a better model. Maybe. So here's one I stole from online somewhere. So we have our predicted value, right? Our actual value. Okay. And so in a case with a multi-class prediction, like what we're doing, our predicted value might be B or not B. Okay. And our actual value B or not B. Okay. And when we get it right, we predicted the category it actually is, it's called a true positive. Okay. If you liked the game Battleship as a kid, this is a hit. Okay. If we predicted that it was this category B for beginning of the entity, and it's not, it's called a false positive. Okay, sometimes called a false alarm, where you've said it's the thing, but it's actually one of the other ones. Okay? In statistics, it's called a type 1 error, right? Let's say we predicted that it's not B, and it actually is B. That's a type 2 error in statistics, but that's a false negative. It's a miss. Okay? You missed it. It was the category I'm interested in, but I said it was something else. And then a true negative, or sometimes called a correct rejection, is when you get it right as the not B. Now we'd have to do that for each one, B, I, and O. Okay, and then multiply that by the fact that they also have the type of entity with them. So this can be a lot of categories. So we won't print the big tables. Instead, we'll print the classification report where we can see all the scores at once. Okay. So to kind of summarize that, if you didn't get it, true positive are instances of the target category, the label you were interested in, when it was predicted and it actually is. So getting it right. False positives are when it's the label you're interested in, but you got it wrong. It's actually not that label. True negatives are when you say, well, it's not this label, and it's actually not that label. So not B in both cases. And a false negative is when you miss it. You say, oh, it's not B, but it is. So let's look at how we can calculate all of our scores. Well, accuracy is fairly easy, right? It's the overall of correct predictions divided by the total number of instances. So true positives plus true negatives. Those are the ones we're getting right, hence the true part, divided by the total. Precision is sometimes called positive predictive value, but it's the number of times you were right for the class you were interested in, so B. Okay. And so this is the number of true positives. I got it right. I guessed that it was B, and it was B, divided by the total number of true positives and false positives. So this will also tell us how sensitive we were to true positivity, so to speak. Okay. So how good am I at finding the category I'm interested in when it's there? Recall is sometimes called actual sensitivity. This is the percent of true positives actually captured. So these are the times that you said positive on the bottom, and these are the times that it actually was positive. So they have slightly different denominators here. And so this is true positive over true positives plus false negatives, the misses. So you have precision, how much when you guess positive, it actually is positive, and recall, how many times when you guess positive that you didn't miss it. Okay. Now, F1 was used because sometimes people don't like having quite so many numbers, and so it's a harmonic mean, because precision and recall don't have the same denominator. So you can't just like add up true positives. Okay. And so the harmonic mean is 2 times precision times recall over precision plus recall. Okay. And it kind of gives you an average score you can look at. So a general Python pipeline for machine learning. Okay. Import all the packages, put those at the top because the order can bite you in the butt, which happened when I was making these slides. So put all those packages at the top of the document. Okay. Create a blank model, an empty model with your algorithm. Okay. Fit the data to the model. Use the model, apply the model to the features, might be a better way to say this. So this does assume that you have done all of your normalization and feature extraction. So this is at that point in the picture where we have the model. We have our features, build myself a blank model, put the features and the prediction classes into the model, and then predict from your model, predict the categories for that testing data. And then calculate the model performance from that testing data. So let's try one. We know this data is already clean, so we can kind of skip that step. Okay. And we've put it into this words and tags format. And there should be, I think it's highlighted weird because of the way I did this, but it's a list of words and then a list of tags, or a list of tokens and then tags. Okay. And from the book, we can then use feature extraction on these words and tags to create these set of sequences. Okay, so we've cleaned the data or normalized the data. Now we're going to extract our features and create a sequence list as our predictor. Okay. You could also use simple formatting. So could I figure out which words are entities one at a time? Yes, certainly. We could convert this data into just literally use the token to predict the outcome. Okay. That would be good, but it would not generalize ever. Okay, it would learn that this token is this outcome. Okay. All right, so feature extraction. Each word in this example for this type of feature extraction, this is not necessarily a normal type of feature extraction. This is the feature extraction for sequenced data. All right, so each word is converted into a dictionary of features. Each sentence is a list of dictionaries. And that is great when you use that sequence for prediction. So let's look at that code because it looks scary, but it's not too bad. So sentences to features. So what it'll do is it'll loop through each sentence and convert it into this nice sequenced format. Okay. So it's going to part of speech tag the sentence from NLTK. And then for each item in the sentence, it's going to take the word, so the first item in the sentence, sentence I is item number 1 in our case, or item number 0, and create a little dictionary, curly brackets, of the features. Okay. And so the word features tag, that's keyword here. So word feats tag here means that is the keyword in our dictionary. And it's going to plug in the tags. Okay. And so it plugs in the tag for that particular word. If that word is first, it gives it a specialized tag called sentence. So this is the start of the sentence. So it marks which one's first by saying, here's the S, that's the start of the sentence. If the word is second, it says, okay, the previous tag, the word before it, is the one directly before it. So it'll go back one. Okay. If else here, right, it will do the one right before it. Okay. If the sentence has things after it, it'll say, okay, well, here's the next one. Else, end of sentence. So what this does in kind of a complex format is it essentially says, okay, if the word is first, then the previous tag is sentence, because that's where it starts. If the word is last, the next tag is sentence. Everything else gets the one right before it and the one right after it. So you have the tag, current tag, and the one before and the one after. So this is a window of 3 words or 3 tokens. Okay. It's not a lot of context, but it's a good amount of context. Okay. And this is one reason why we have to use a specialized algorithm, because that is not, most data that we use for prediction is square, okay, or at least formatted, where every predictor has the same number of inputs and outputs. And in this case, we have we've now made it square, 3, right? Previous, current tag, next tag. Okay. All right. So this get features one just calls this function up here, right? And says, okay, there are features and there are labels, and run over this one sentence at a time and return the features and the labels. Okay. So I've created my features and my labels using this function, which is just a wrapper to make this one run, right? And created, features and labels for my training data and my test data. So let's look at what that looks like to kind of figure out how that is saving the data. Okay. So let's see here. What is it in? Oh, it's the whole thing. I only printed out the first one, right? Feature 0. So that first word, its tag is NNP. Okay, that means it's a proper noun. The EU is a proper noun. The previous tag is sentence. The next tag is past tense verb. Okay. And so then we move on, where all of them have, each predictor has 3 little dictionary key tag pairs. the tag for the current word, the previous tag, and then the next tag, and so on. So check out what's happened here. We now, for each sentence, have a string of predictors that have all three, kind of the three little window, but no words. So this training does not learn the individual words. That actually makes it rather agnostic to the language itself, which is nice, because anything that you can do that is language agnostic is perfect, because that means I could do this in German and it wouldn't care as long as I had the tags. Now, for each of these little sequences, we have what tag it should go with. So this three-part sequence is be org, O outside, be misc, O, be misc, O. So in this particular sentence, there's none that are more than one word. They're all one word entities. So conditional random fields, if you like a lot of math, this article is for you. If you don't want to learn some math, let me tell you what the basic idea is. So the idea behind a conditional random field is that the order of the inputs is the most important thing. And so what we have here is the actual tag, the one before it, and the one after it. So we have a three-part sequence with the order of it. And then we have the next one as well, ordered. And so the prediction of the next word is based on the ones around it. And that's called a linear CRF. Sometimes Markov models are programmed where they don't care about the order is important, but it doesn't quite go linearly. It can go backwards, forwards. So this is called a linear CRF because that's how we read, right? In order. And this is actually very similar to the way that Word2Vec works. Okay? And so we'll consider Word2Vec later. It's a very popular model developed by Google. If you've heard of fast text, that's Facebook's version of Word2Vec. And so both of those use this idea of like word chunks, and the order is the most important part at predicting what comes next. Okay. All right, so let's apply that to features. Now, the example part of this section from the book does not run, so I made it run. And I'll show you really where it's wrong, but they wrote a little function to do this pipeline, but I'm just going to show you one part at a time. And so I kind of relabeled stuff because I think it's a bit clearer, because most tutorials use this ytrain, ydev, xtrain, xdev in them. So we're just going to relabel the data for funsies. We're building a blank model. So here's our CRF algorithm. Now I have this try except because there is a small bug in CRF where it will like throw some error message, and this just makes it not yell at you because it runs fine. Okay. But this looks and is basically how scikit-learn's API works. So you do model.fit, and that creates, I'm not having to save it or anything, that creates our model where the features are combined with the classes, and we can use that to predict the next set of features. Okay. So .fit here, we put in our prediction categories, xtrain, remember, which is our new feature set, and ytrain, which is the outcomes. Okay, so we're predicting with the three-part sequence to each outcome. Okay. Now, how do I tell if that's any good? Okay, I've made this model. Now what do I do with it? Okay, like model. Well, I use that model to predict the testing data set or the development data set. If this model were any good, I would then use it to predict my new data where I don't have the answer, but I want it. So I think sometimes, and myself included here, in these videos or these tutorials, people show you how to build these models and then they don't show you what to do with them. And so the answer is you use crf.predict on the new data that doesn't have the answer, and you want the answer in it. And we do this in class and use that information to look at other data, but y'all aren't with me during class, you're here. So you would take this model, if it were any good, and use it on a new data set, which has to have the same normalization. Now, this is where it all goes sideways in the book. One issue with using scikit-learn's classification report is that it doesn't like sequenced data. Okay. And so it won't match the number of items that you think you have, because we may have 6,000 sentences, but we've converted those sentences into sequences. So we have more training data than you think. So we're actually trying to predict the individual tokens, of which we have 46,000 in the testing data set. Okay. But the Y, the answers from Y are built into this list of list format. Okay. And so we have to basically flatten those out. So flatten's a really nice function. When you have lists of lists, it just like unlist. This is the unlist function from R, which I wish I'd found the other day before class, but I now know it, right? So flatten. And that is in the CRF, scikit-learn CRF suite. Okay. And so I'm flattening out the development answers. I'm flattening out my predicted answers. And then now I can use classification report like no big deal. So Y true is the development answers. Y pred is the predicted answers. The F here just stands for flat. And what we get is the overall accuracy. Okay, so overall my accuracy is 89%. Just pretty darn good, because that, I mean, we're predicting what, 9 tags? 1, 2, 3, 4, 5, 6, 7, 8, 9 tags. So to get almost 90% correct is really good. People have in their heads some magic number that they think accuracy needs to be for the model to be good. And I'm going to tell you right now that it's wrong. Okay? You need to stop and think about what the field specific areas best results are. Okay. And in NER, that's wildly variable. Okay, if it's part of speech tagging, it's like above 90%. Right? In NER, whew, out the window. And also think about how many tags you have. Because chance here would be 1/9. So we're doing way better than chance. Okay. Chance in a spam versus not spam prediction is 50%. So think about how many categories you have, because that changes what chance is, and what's normal for that very specific area and type of data. Okay. So I don't have an answer for what accuracy do I need to meet for the model to be good, because that is highly dependent on the type of data. Okay, that rant aside, you do want to try to predict all of the categories. So what is driving our overall percent correct? Check it out. There's tons of O's, tons of them, because there's tons of words we just do not care about when it comes to entity recognition. All those filler words, all that jazz, don't care. So that is really what's making the model look good, because we're getting those 96% correct. Okay, because it's a large majority of the data. Look, it's 38,000 of the 46,000. Okay. The other ones, we're not doing quite so great. So we would probably want to see if we can figure out another method to improve our training for these other options. So we're getting locations kind of right? So I remember that chance is 1/9. So 54% here is not terrible. Miscellaneous, not great at all, but it is one of our smaller categories. Our two smallest categories here, we're getting not very good. I don't even know what chance is. 1/9 is less than, it's wait, more than 10%. I'm going to calculate this 1 second. 1 divided by 9, 11%. Okay. So we're getting inside miscellaneous at exactly chance. So that's not great. Definitely some room for improvement. I is hard, okay, because I's don't happen very often with these other ones, but they happen way more frequently with person, and you can see that the frequency in the data set also helps with the prediction here. Okay. We're also getting B, the start of person, much better. Okay. So we're doing pretty okay. Okay. This model would probably miss a good number of the second words, but might get the first word of your entities. So if you want to do more, there are some examples in here using both spacy and BERT to train. Warning, enter at your own risk. I haven't tested these, and things change pretty quickly between publication and Python packages updating. So that is what took me a while to get this one to work, was getting the classification report to spit out. Okay. So can we just use a pre-trained system? Like, do I have to do this training? Of course. So what are some issues with NER in general? Okay. So terms and entities are constantly changing. If you are interested in pop culture at all and you're wanting to do some entity stuff for that, good luck, because that is constant. I feel like the old lady when I watch or look at some of these like BuzzFeed, I'm like, who are these people? Right? That's how an entity model works as well. So it will constantly have to be adding things, updating a model. But once you have a model in place, you can update them. You can retrain them or add new training examples to them. Okay. They don't have to do the whole thing over. Okay. And so the real systems, when people put this into production, okay, is that they use a combination of rule-based heuristics and machine learning. And so again, it's better if the machine learning algorithm is agnostic to the words themselves. And so the rule-based heuristic is how you might label the data to train more and more examples. Okay. And so rule-based heuristics also can help fix inconsistencies. So if you get New York, you could change that to, well, that one would be hard actually, because you've got New York the state and New York the city. If you get something, I don't have an example there, but if you know that something is an organization, but it tends to be tagged wrong, you can fix it by using a rule-based system. You know, if entity is this, then tag is org. Okay. Those kinds of rule systems, dictionary lookups, basically. Okay. And NER is especially sensitive to the data it's trained on and the structure of the data that it's trained on. So what that means is that the data has to be clean and it needs to be sentence-like. Okay? And it runs much better if both of those things are true. So if you're using something like a PDF or OCR extraction, that's not always perfect, and that can really mess up the idea of sequencing. Okay. And so it's also sensitive to all of the pre-processing steps. Okay, the normalization procedure, the extraction of the data into text, the normalization procedure, and the feature extraction, which requires part-of-speech tagging and sentence tokenization. So there are a lot of places that small tweaks can really affect the outcome. Okay. And I think that in my previous versions of this course, we do an example, we're doing classification, and we change some of the normalization and then change which algorithm we're using and then change some of the feature extraction. And it's amazing because each different data set, it's a different thing that improves prediction. And that's true here too. Okay. The pre-processing steps to the normalization to the extraction can all change how well your algorithm works. Okay. And then you have to assume that data, that training data, is representative of what's actually the data you're going to use. And then that data that you're going to use needs to be processed in exactly the same way. Okay, so there are a lot of places this can go wrong. All right, so we could use a pre-trained system and add more to it when using what's called active learning. And so this is where you would find new prediction labels or classes and then add them to the system. Okay, using either a new machine learning, like training it on new examples, or adding more rule-based heuristics as that arises. So let's do a couple of other topics, and they're all kind of tied to how can we make this idea of NER better, right? So we're going to get into Snorkel as well, and how you can, if you don't have training data, you're like, okay, but there isn't a Kaggle data set for what I'm interested in. What do I do? Okay. But named entity disambiguation is really cool. This is essentially the kind of like thing where you can click on it and it'll pull up Wikipedia, right? So knowing that that this thing is an entity, right? Alex Smith, for example, and then knowing that that's this person connected over here. Okay. And one of the issues with the way that we use language, and this is really true in the knowledge graphs section for next week, is that we have a bad habit of using what's called references. Okay. And so here's the example, blah, blah, blah. No reason to expect Alex Smith would be in his current position. So that pronoun, sometimes called anaphora resolution, is related to Alex Smith. Okay. You're referring back to that person's name. And another thing that you might do is use the full name the first time and then just the last name every other time. So a lot of things about the way that we, especially in English, tend to write and to speak that make disambiguation difficult. So the first thing you have to do to get disambiguation is do the recognition or the key phrase extraction to get the things that you're trying to disambiguate. Okay. Then you have to figure out what those things refer to in the real world. And a lot of people just pay for this. Okay. And so if I said Lincoln drives a Lincoln Aviator and lives on Lincoln Way, all three of those Lincolns are different things. And our, even our part of speech tagger can't help there because they all would get labeled as proper nouns. So understanding those are different things is quite difficult. Okay. So when we put together NER and NED, we get what's called NEL, because there are not enough acronyms in this lecture, are named entity linking, which is essentially the disambiguation step where we link all of these objects together. Okay. And that helps us with relationship to extraction, which we'll see in the next lecture. Okay. Well, to get named entity linking, we need part of speech tagging, named entity recognition, and key phrase extraction. So that's why this lecture is in this order. Okay. We also probably need some parsing. If we can understand the subject, verb, objects of sentences, we can start to link them together. So if I know that this is a pronoun and it's referring back to this noun, that makes the linking a lot easier. Okay. Co-reference resolution to put together all the names of the same entities. Okay. And then link that to a database of who these things are. Okay. And that's the part people pay for. Okay. So, there's systems like Azure has one with their API because they have all the time and money and data in the world, and you would pay per use. There is a free example. It does have a certain number of hits allowed because I accidentally ran these notes one too many times, but DBpedia has a spacy pipeline. That's really cool. Just don't use it too much. And so you can look at the spotlight here. So it explains how to use it, but it's actually quite simple. Okay. So you import the two libraries, you load your spacy model like normal, and you do what's called add pipe. So you would add the spotlight pipe to it. Tell it to run on a document. Okay. You print out text and label and entity.kb ID for each entity. Okay. And so what we have here is we have USA, and then it says, here's the resource for that. So this is a link that you can click on. Boris Johnson. Okay, here's a different link. Coronavirus. So it's essentially pulling it and linking it to each object in the dictionary. Okay. The raw result tells you how much similarity there is. So it's only printing one of them here. Let's look at this one. Okay. And it's linked to the United States. It says that this is a place, country. Okay, this is what's called a schema. So it just tells you what kind of data entry it linked it to. It's a populated place. Right, it keeps going over here. It's surface form, USA, right? And a similarity score. So here's how much it thinks that is what US should be related to. So 0.9965. Okay. And so we can see how close I thought we were. So that's really cool. I would say that this is more of a system that you should pay for. I think if you use DBpedia, it does have a certain max number of API calls and would be good for really small projects. Now for relationship extraction, okay, so now we're trying to pull all the things out, right? It's where you take that entity data and its linked object and figure out the relationship between them. Okay? So here's a sentence about the CEO of Microsoft, right? And an example of the types of links you might make. So it's an employee. This person is a person who's an employee of Microsoft, right? So that's the orange here is the relationship. It's a citizen of America, citizen of India, or Indian, I guess, because of this here. And we could say the other entity relations here could be that this person, right, was also tied to employee of Microsoft. And so we could build that whole relationship of the text together. Okay. Now, this is really hard. Relationship extraction is a lot of code, and you'll see that in the next lecture. And it can be really useful for building a knowledge base, but it requires a lot of careful thought about how the relationship is going to be represented in the text. So we're going to use an example in this lecture from Snorkel, and then we'll use an example from the next lecture about news data sets. But I would say the hardest part about this is figuring out how that relationship is represented in the text. Okay. So is it always like employee of? Like, how do you figure out how that is tagged from the text? And so relationship extraction is really interesting because it's useful for questioning and answer systems, because if you can extract the relationship between things, you can figure out the answer to the question. Okay. But defining relationships can be tricky. Okay. And so like in a medical field, for example, the relationship might be type of injury, cause of injury, place of injury. Okay. But in the business field, it might be people, job types, locations, and services for the company. Okay. And for me, that type of academia one might be institution, type of research, grants achieved, and more, I should say, et cetera, on the end. So relation is not like like here's a list of relations to use. Okay. So most relationship extraction is done with text patterns, right? So person, CEO of organization, may indicate who and what they do for an organization. That's easy to program, but it's difficult to capture the sort of nuance that happens in text writing, because I might say the CEO, comma, person, comma, of Microsoft, right? So the different ways that we write these things can be tricky. We can also do supervised classification. So first thing, are these two entities related? Yes or no, right? And if you say yes, then what is the relationship? And that's a multi-class question. So there are a couple of ways to approach this. I would say the first one is the most common. So what could our features be? Okay, the features could be the labels themselves. So the NER label, first one I got is organization. So here's what I know organizations have, right? They have CEOs. We could use the syntactic structure of the sentence. So the prepositional phrases and direct objects in a sentence would lead us to who's doing what to whom. We could also do neural network models using those individual words in sequences. Okay. And a lot of folks use, there's a Wikipedia data set that are, they first train it on these huge, like kind of global data sets to help with the large sample size and getting the patterns and structures that are available in the data, and then adding specific area examples to the data. Okay.